All right, so next up for NASA Hacks, we have Lucy Dew and Charles Dandino. Lucy is a mechatronics engineer at JPL. She received her bachelor's and master's from MIT in mechanical engineering, where she helped found the student-run makerspace. And she has competed on both seasons of the new Battlebots with Overhaul and Sawblaze. Charles is a mechatronic engineer at JPL with experience on Curiosity and the next Mars rover, the Mars 2020, CubeSats and R&D, and he's currently working on the Asteroid redirect mission, which will end us all, hopefully not because of him. Okay, so can you please give a round of applause to Lucy and Charles?
And we're here to talk to you about NASA hacks. These are ways that NASA has used software or hardware in slightly unconventional ways that you might not have thought of in the first place to either solve an emergency problem or to be a little bit more efficient with resources. So everybody's heard of Apollo 13, probably. For Apollo 13, the oxygen tank in the service module exploded on Apollo 13's way to the moon. And so the lunar landing was canceled, and all of NASA was focused on trying to get the crew back safely to Earth. So one of the things they had to do was move the entire crew over to the lunar module to save energy. Problem was the lunar module wasn't really designed for prolonged spaceflight, and there are a lot of problems leading up from that. NASA's people on Earth decided to do some calculations, and they figured that the lunar module did actually have enough power to propel everybody back to Earth, barely. But one of the big problems was the lunar module only had CO2 filters that was designed for 2 men over 2 days, rather than for 3 men over the course of 4 days. So they had a bunch of extra CO2 filters for the service module, but not for the lunar module. Hilariously, the filters for the initial command module were square, and the barrels for the ones for the lunar module were round. So they had the literal problem of trying to put a square peg in a round hole. And they fixed this with a lot of duct tape, an extra spacesuit, and some plastic bags. Who knew? So another problem that NASA eventually ran into was the Ares 1 rocket. After the whole rocket was built and they were going through testing, they found out that during the final stage of launch, the vibrations in the final stage actually caused so much movement in the astronauts that they weren't able to read the digital display. And if they can't read the digital display, they can't do their jobs. And that's a problem. So at first, NASA panicked. They were like, oh my God, this is $1 million problem. How are we going to fix this? But the engineers did their jobs and found that if they just put accelerometers, basic accelerometers, on the seats of the astronauts and measured the frequency of vibration, they could blink the digital screens at the same frequency, and the screens would be perfect. You can see crystal clear. So it was $1 million, possibly $1 million problem that was fixed by just a couple accelerometers. So this one's not really a hack. The ISS solar arrays were designed for this, but it's kind of an example of using something, using things for multiple purposes. So for the solar arrays, you can actually move them, articulate them in different directions. Part of this is so that the solar arrays can be more efficient and face the sun. But another part is just because you're in space doesn't mean there's not any atmosphere at all. So you can actually use them as sails. And the ISS can adjust the altitude slightly based on the angle of these solar arrays. So that way you don't have to use propellant to make slight adjustments, and propellant is really, really expensive. All right, so a lot of times when you go to space, you have a very small amount of space to do, and eventually you want something big to come out, usually. So large antennas stored in very small volumes. So this example is for a CubeSat, which is shown in that corner. It's the small blue square, and we needed antennas 4 antennas that are about that long to scale. And if you think about something that you want to be really long, pretty rigid, pretty strong, but can store in a small space, a tape measure is a really perfect example of this. So you can, if you see in the picture over on the bottom, that's the yellow circles are tape measures coiled up. And the idea is that they're coiled up until they're ready to deploy, and you just kind of let them all spring out. And they'll look like the picture on the top. So here's a picture from one of the tests that they actually did. It springs out pretty well. It gets a little chaotic after this in the full video, but eventually they kind of all stop bouncing and even out, and they deploy perfectly. So tape measures in space. Good idea. And now for Charles.
Hey. So I'm going to move around a little bit. So I got to move.
You should take this way.
All right. So do we have anybody in the audience who is a fisher, an angler, if you will, fisher folk? One, really? Nobody else? Like, I got a half raise. Thank you. All right. So does everybody at least know what a fish hook looks like? Kind of like that. It's got the barb. All right. So if you're used to fishing, you know that the fish hooks are great for catching two things. One is fish, and the other is everything else that you don't want. Great for logs, seaweed. And so taking that kind of problem and turning it into a solution, when you need to grab something that you don't really know what it is, you use the thing that grabs everything, whether you want it to or not. But one hook might not do the trick. There's a good chance that it will, but there's a good chance that it won't. So you can just increase your chance of success by putting a lot of hooks. So this is one cassette of hooks, and you can see over here, that's a lot of cassettes. Each individual hook is compliant and can articulate on its own. So when one of these catches a little bump, or an asperity, if you will, it will hold on to that and continue to flex away as this gets pulled in. So I guess I should back up for a second. The way that this mechanism works is that all of those cassettes start raised, and then they go down, pull in, and move up. And that provides a way for this thing here to stay against the asteroid. You're thinking, like, why do we need to snag an asteroid with fishing hooks for any reason whatsoever? And part of that is, we need to redirect them with the asteroid. We're not going to redirect it by fish hooks. They're just kind of snagged in there. We're going to drill. Thanks. We're going to drill an anchor into the asteroid. But again, think about drilling. If you're drilling with something, you're going to push into it. Now imagine you're drilling on a skateboard that's on an ice rink that has air bearings because it's space. So that frictionless thing that you all really loved, I loved anyway, in high school, that's real. That's in space. So you try to push with that drill, and you're going to keep pushing away and away and away, and now you're floating. And that's the end of your mission. So these hooks kind of hold that in and keep it moving, or keep the drill engaged. And just as a side note to that mission, because it is the one I'm working on, I like it. Once you're anchored in, then you just pick up a boulder off the asteroid, wrap some robotic legs around it, and bring it home. So that's fun. So testing this out, how do you test out whether or not this device that you're going to use will actually work on something that you know nothing about? In this case, an asteroid. We've never sent anything to an asteroid. I mean, we got some pictures. The Philo-lander didn't quite anchor, so we know what doesn't work. But that doesn't give us a whole lot of information on what will. So based on some measurements and scientists doing a bunch of things that I don't fully understand, we have some compression strength estimates. And these estimates will kind of help direct approximately what this material should look like. So cohesion and compressive strength are two important things to give you a sense of like how well we know these things. Lunar regolith goes from 0.1 to 1, snow 0.6 to 6. So the variances on these are huge too. So the target we're trying to hit is a bit nebulous. But how do you make the surface of an asteroid with concrete? it's a rock, so we make our own rocks. We make our own rocks always with concrete, but the rocks are a little strong. One of the mechanisms that makes rocks on Earth so hard and rock-like is the gravity and the compression and things and mechanisms that allow everything to compress it all together, and those simply don't exist in space. So we expect it's going to be much more flaky, much softer, and but still very brittle. So the foam concrete does a great job. It also provides a nice texture for those fish hooks to grab into. All right, so another issue that we face is trying to figure out how well the wheels on the Mars rovers are working. I'm going to focus on the MER missions, the Spirit and Opportunity rovers. They're moving along, and things are going pretty well. They're in some sand, and we're kind of like, how well are the wheels moving? We say we're rotating one full rotation. We know what the diameter is. We're traveling about that far, but how good are we actually doing, and how can we measure this more accurately? One way to do that is to look at your tire tracks. And the MER wheels have ridges for traction. They're all evenly spaced. And there's one spot on the wheel that's completely different than the rest of the spots, because that's how the rover was anchored down to the spacecraft. So during launch, while everything was shaking like crazy I don't think it was on an Ares rocket, but if it was, shaking like crazy, that vehicle doesn't flop around inside the spacecraft. So those are preloaded with pretty large bolts that then pop off. So that structure is more beefy. And as it rolls along the sand, it creates a stamp as it goes along. So we can go back and measure the distance between those stamps and try to calculate, for this input that we gave saying move forward 100 feet, did it actually move forward 100 feet? Where did it slip? And mapping that terrain to what is and is not traversable is very important to avoid getting stuck. It only goes so far. It's difficult to not get stuck in terrain that you're not familiar with. A very extreme example of this is right here, where we're kind of dragging one wheel. So you can see the difference in the tracks. But over here, you can see right here, this roughness is the launch lock. This roughness is the launch lock. So you can kind of map out how far the wheel is actually turning. And you can, based on the way the sand is bunched up, it's pretty likely that this wheel was actually kind of doing one of these rather than a nice smooth motion. So it was kicking up a lot of sand. And keeping in line with that, when the Curiosity rover was being designed, they took that same odometry feature, sort of hack, if you will, and incorporated it. This Curiosity, as we all know, well, maybe everybody know that Curiosity came down from the sky crane? Yeah, seen that video? If you haven't, check it out. It's cool. There wasn't a launch lock reason for the wheels to have an unusual spot, but because we were able to use that to our benefit for the MER missions, it was incorporated for the MSL mission, if only for an excuse to write JPL in Morse code, because JPL is a subcontractor of NASA, and they don't like us putting our name on anything. So now we roll around and tag Mars all day, every day, just JPL across the. You're welcome. So this gets in a little bit more to what we have kind of been looking at here and exploring is a little bit more traditional hacks. This, for example, is a Hot Wheels car. It's a Hot Wheels car that's been modified. You can actually see the wheels in there. And these are some 3D printed parts that make the modifications. This system here is the that's actually a robotic leg, or it's a leg. It's the Rex system. So even though that just spins like a wheel, because it has a flexure here, it causes this robot to kind of bounce a little bit, and it's actually considered a legged robot. This isn't the most impressive implementation of that, but Boston Dynamics has some good ones. I think Penn has a lot of interesting robots that make use of that system.
If any of you watched season 1 of Battlebots and saw one of the featured rumbles, the robot overhaul, which is one that I worked on, was a walker shuffler robot.
Nice.
So not only space uses those.
So yeah, but for this small compact package, we can make all of these springs and gears and the chassis and the housing, but it's a Hot Wheels car. That somebody already did that, and they did it really well. They put a lot of effort into it, and they made it mass producible. So why not build off that? Why not hack this hardware to advance your idea? And the way that fits into the NASA structure, I'm going to give you a little peek inside, is that there are thousands of people at NASA that all have brilliant, brilliant ideas. Just fantastic, amazing ideas. And the NASA budget is limited. So we can't chase down every idea. So you got to prove that your idea has some legs. It can actually go somewhere. And the best way to do that is by modifying something that's off the shelf and really just focusing on uniquely making that one aspect that is a step above what the last thing was. So for example, if you want to show that your sensor package can get around desert terrain and provide useful feedback, you can spend a bunch of time making your own custom robotic rover, or you can go to your kid's sandbox. I happen to know this engineer. He did actually borrow this from his kids. And this is just an off-the-shelf remote control car. It's $30. When the wheels get going, they have these tiger things you grip, and you can't slow this thing down. It'll go over all kinds of rocks. So it's perfect for taking the sensor package around rough desert terrain where it needed to perform its sensoring. That's where my knowledge drops off. I don't actually know what that thing does. But I really appreciated that it was well fastened to its carrier vehicle in a very time and cost-efficient way. Similarly, you need a small gimbal for your camera. A lot of this is just 3D printed parts, and then this gear system, you can custom spec out your gears and order them, but a gear train and geared down systems within toys are so common and so well made that there's no reason to not use that functionality. All right, and this is going to wrap it up with the Galileo mission. So Galileo had hopes and dreams of being a beautiful, blooming flower like this, but things didn't go quite right, and it became a much more grainy, not fully deployed image like this. So the high gain antenna right here, which provided a lot of gain in the design, does not provide nearly as much gain when it's not quite open. So kind of like back in the day when you had to pull out that antenna for your cell phone, depending on how far back in the day we're going. It could be a fairly large antenna. Your antenna matters. It matters a lot. So with a only partially deployed antenna, we're trying to talk back and forth to Earth with not only the delay that comes inherent with spacecraft, because the speed of light traveling between planets, or sending communication between planets, even at the speed of light, is still pretty slow. To couple that with, I'm going to say something, it's going to take you 10 minutes to hear it, but by the time you hear it, it sounds like I'm talking on a cell phone in the basement, and then you come back like, what? And then I send something to you, and what? And we can do this forever. But the change in the mission structure also led to a change in the resource balancing and packaging. Suddenly the bandwidth, because it was now much more reduced from what it was originally supposed to be, was the critical aspect of this. And the onboard processing power, which Galileo was kind of a while ago, was not that great to begin with, there's a lot of it, because you're not sending a lot of information back and forth, and that computer's going to sit idly for a lot of time. So rather than sending a lot of data, use that processing onboard processor to do data compression in a way that hadn't been done before. And I'm more mechanical, so that's where my knowledge of what exactly the fix was kind of drops off. But they used data compression to maximize the resource utilization and still have a very, very successful mission with a huge amount of science data. And with that, we provide you with references. It's not all totally made up. And that wraps it up. A little bit short.